Well, hi everyone. I'm Eduardo Franco. Today I'm going to talk to you about a little bit of how can integrate manifolds on GPU and physics simulations. Okay, Symmetry X is currently a package we are developing, and it stands for a motivation that when I was in college, in the first years, we are working on with these deep math equations, and finally we arrive at the equation of motions. And at the time, we could visualize this kind of stuff, but when you dive in a little bit more and get into more complex physical systems, the hours waiting for the code to run and the tedious stuff, it became a little bit tired, right? So when we dive into a little bit this, we discovered GPU, Julia, and obviously high performance computing. And that's why when you start to code a little bit more, you understand that these capabilities are raising the infrastructure or physics simulations. So integrating this with CUDA.gl, we decided to create certain types of kernels which contain each the geometry of the manifold, and then we apply the physics inside of them to make some kind of simulations. Right now, you are going to see a little bit of the simulations we have working on and how we can apply this to more complex physics. And well, of course, this will motivate all of you to, well, in fact, try this package. The first one, we have like a charged particle on a torus. This animation runs like in under 2 seconds over 1,000,000 steps. 64 particles around the crater of the torus, which with initial velocity, you can assignate the position vectors, the velocity vectors, and the charge vectors as you wish. In this case, we are just having you some kind of the equation. Here, you can imagine like could be plasma physics or condensed matter 1D lattice. This because of the ring you are seeing this approaches an harmonic oscillator and the normal modes of the torus. Also, you can identify another kind of structure, the ellipsoid, or where here you can see how it's a self-organization system where the system tries to balance out the charges. And, well, in fact, this is not only applies to classical physics, this will also apply to soft matter. If you can interact with this kind of particles at colloids, it will be another kind of physics. Also, I've talked about the manifolds, but you were seeing the 3D representation. In fact, the 2D manifold of the torus is just the theta and phi 2D space. So what the program does is the kernel, in fact, do the simulation over the 2D space and then just plot it or transform the coordinates to the original space.
Does the physics depend on the embedding in 3D?
Of course. The embedded of the, no. The physics depends of the metric of the system. Yeah, right, I forgot to mention the manifold is like, you can imagine the manifold as a surface of the structure that locally is flat, but in general is curved. So all the physics, all the interaction will be changed of this the structure. In fact, the space-time is also a manifold, right? So we are working on implementing also this kind of physics. Not just the interactional physics is on the surface, it could also be an external surface, like this with an external potential A, that could also interact and modify the trajectories of this structure. This not only applies to Lorentz models that you are seeing here, but also to active matter. Active matter is a solid chain of physics, which involves also a little bit more like the Brownian motion, and this other potential could be like interactions of the surroundings, right? Not only we have particles, we also support some kind of fluids. or any kind of quantity that we want to see how this works under the surface. This not just applies to water, well, to fluids, but also could be some gases. That's why statistical mechanics can also be used in these examples. You can take the entropy as the curved heat, and then you can understand what is happening around the curvature. Finally, other of the examples are the Lattice Boltzmann method. It's another kind of algorithm to improve some kind of stochastical mechanics systems, and yet also this runs on GPU. All these experiments that I'm telling you right now runs in less than 2, 3, 5 seconds in a GPU, which is a 450 in my computer, and it doesn't require a lot of complexity. Yeah, it's just for, it's in fact a wrapper around the CUDA.gl, but it adds the physics around it. So right now, Symmetry X is just like this little package. I'm working on it, but tomorrow we are expecting to add more manifolds, more geometries, and eventually more physics to make this kind of knowledge more democratized, this kind of knowledge. And also, all these systems that you see, they are already a connected paper to one of them that already have been published by some authors in the past, but we just recollect it. Thanks.
Hi, thanks for such a wonderful talk. So I was curious, here do you really need the GPU speed up because you're simulating on a manifold, or is it more so because you have some large number of particles you're simulating?
Yeah.
Or both, maybe.
Yeah, that's right. In fact, if we try to simulate each one of these systems, the CPU could be worked on, but the time complexity and the time that you are waiting for the results and the visualization will be very much upper, right? In fact, if we connect this with GLMACI, at the time the computation is doing the simulation, it in real time is displaying the image. Okay, so it's a good question, but the GPU accelerates these computations, and it doesn't need or requires, in fact, a GPU, but it allows us to make this much, much faster.
I have two questions.
Okay.
First, you mentioned CUDA.jl.
Yeah.
Is this limited to CUDA, or did you use also kernel abstractions or something like that?
No, at the moment it's just CUDA.gl. We were working to use also kernel abstractions, but we didn't have AMD the computer on, and also didn't have the Metal on for Mac, so we couldn't make it. But in the future, we try to improve this to add those kind of GPUs.
And my second question is, have you looked at problems that are so big that you need to use some distributed computing and break them up across nodes?
Yeah, that's why, because, for example, if we look take for example these 256 particles, it's a matrix of these particles with each one representing 2 vectors of the position at the time at the manifold, just theta and phi, and also its velocities, right? So this this matrix increases at the time where the particles increases. Evidently, we have flow 32 allocated to just one particle at a time, so we will need more than 3,000 particles in some simulations to overhead the capabilities of a GPU. But in theory, we could make some statistical models like gases corresponding on these ones. with millions of particles, and then, yeah, we'll need some dynamic allocation on other GPUs.
But you haven't done that yet?
No, we haven't done that.
Do your manifolds have to be two-dimensional?
Sorry?
Is it only two-dimensional manifolds?
At the time, the only two geometries we support, yes, is the ellipsoid and the torus, but rising up to other 3 or 1 dimensional is just reconnecting all of the other stuff. So it's not that hard, but yeah.